Okay, so in this video, let's actually get down to a full multi-layered perceptron, and we'll see how to train your weights or your neural net, how to train your neural net in a multi-layered perceptron. Okay, so I've drawn this figure. Now I know this looks a little complicated. I'd recommend that if you're following this video, you draw it in your notebook as well to understand better. And it looks a little complicated, but it's not complicated at all. It's very easy. Okay, all I'm going to do is I'm going to apply chain rule from your higher order calculus that you learned in school, right? That's all I'm going to do, and that's all that training a multi-layered perceptron or a deep neural net is all about. So let me first explain what's going on over here. So look, I have inputs, okay, xi1, xi2, xi3, xi4. Okay, so the input, I'm going to denote it as xij, where I is the data point and j is the dimension, right? So if you have a data set, you have data points, right? So this is the data point and this is the dimension j is 1, 2, 3, 4, right? So the dimensions are the columns and I is the data point, which is the row. So the input goes in over here, right? It goes to the first perceptron. So I've denoted the activation function on the perceptron by f11. Okay, now f11 is the first one is, so if I have fij, right, I basically tells the layer number. Okay, this is the first hidden layer, this is the second hidden layer, this is the third layer. So the first number in F, which is I, tells the layer number, and J basically tells the order of the function. Okay, so this is F11 because this is the first layer and this is the first activation function. It's on the top. F12 because it's the first layer and this is the second activation function, which is in the middle. And this is the first layer and this is the third activation function, which is at the bottom. So that's F13. Okay. O11 is my output, all right, because this is the output from my first activation function in the first layer. Okay, so now if I take OIJ, I basically tells the layer number again, and J tells the function from which I get my the activation function from which I get my output. Okay, which is again the order. So this is the output from my first layer's first activation function. This is the output from my first layer's second activation function. So that's how O11 and O12 are defined. The weights, okay? So now the weights are W superscript 211, okay? So if I have to write the weights over here, this would be W2 superscript 11, okay? So now if I have W over here, the first one basically tells from which layer it comes out, and the second one tells to which function it goes. Okay, so it comes from the first function, it goes to the second function, and it's in the second layer. Okay, so that's what the superscript is, the layer number. I'll just write down here wij. Okay, I is basically the function number or the order number from the first layer, order number from first layer, and j is the order number to the next layer. Okay, and the superscript x, order number to next layer, and the superscript x basically tells the layer that I'm dealing with. Okay, so here this is going from the first one to the second one, right? So s will be 2. Similarly over here this will be 1. It's not 2, sorry, it's 1. It's going from the first point to this first function, and it's going to the first layer, right? So this is 1, superscript 1, right? Superscript 1, weight W11. Okay, so that's how I'm denoting the entire neural net. This is important because when I'm training the neural net, you'll understand exactly how I'm going about it. So now I would recommend that you actually just take this diagram down, because when I'll be writing it, you might not be able to see the entire diagram in the picture. So it'll get easier to follow, right? So now to train my deep neural net, I go about doing the same thing that I said the same steps that I followed in the previous, in the previous unit, and in the previous video where I was training a single perceptron. Okay, so first I define my loss function. Okay, define loss function. Correct. So my loss function again over here for simplicity's sake, I'm going to take my loss function as I equals 1 to n yi minus yi hat the whole square. This is the squared loss function. Okay, this is the squared loss. So my loss at a particular point is just yi minus yi hat the whole square. Correct. So basically, I can write this equation as sigma I equals 1 to n li the whole square. Correct? Right? I've just put this over here. Right? So now the second step is to pose the optimization problem. See, every problem in machine learning, deep learning is just a step, is just these three steps. Okay, define the loss function, pose the optimization problem, and solve for the optimization. Pose the optimization problem. Okay, so I basically have to minimize my loss, which is basically have to minimize my loss, which is this, with respect to the weights, the weight vector w1, w2, all the way to wt. Correct? That's my optimization problem. Okay, and now the third and the final step is to solve for optimization. Correct? Now, first, I'm going to initialize my weights randomly. Later on in some video, I'll tell you how people actually initialize weights. There are lots of techniques to initialize weights. But for now, for simplicity's sake, I'm going to initialize my weights randomly. Okay? So, initialize weights randomly. Look, you can't give weights as 0 in the beginning because then you won't have any output. We need to initialize the weights randomly or using some technique. I'm just going to initialize them randomly before I even give it a single input. So I have my wij superscript k new is equal to wij superscript k old minus eta dou L by dou wij superscript k. Okay, we saw this in the previous video. If you don't know, just watch it. Now I have to optimize, I have to perform the conversions, right? I have the conversions over here. This is my convex function. I need to get to the minimum point. So look, I'm gonna, like I said in the previous video, okay, to optimize, look, we are optimizing this deep neural net. Basically what we are trying to do is we are trying to find the best weights. So I have to go back over here, right, from one step to another. I get my output yi hat, which basically gives me my loss function. Correct? This is my loss function. So I have to keep going one step back. I'm going to take it one step at a time so that you understand. First, I have to find my weight. I have to differentiate the loss function with respect to my weight dou w311. I'm taking it one at a time. I'm going from my loss function to this weight w311. Okay. So this again, I have to apply chain rule over here because if you see, I have this function f31 over here, right? So I have to first differentiate dou L by dou O31 into dou O31 by dou W311, right? Why am I allowed to do that? Basically, output is just, O31 is the function, right? O31 is basically F31 of W311 into some input, xn, something. Okay, so when I'm differentiating it with respect to the output, I'm basically taking the function over there. So that is my Dow L by Dow W31, okay? I won't write all of them because there are lots of equations here, but I'll explain how to go about it, okay? This is one equation. My next equation, I'll just write it over here. Okay, so my next equation is Dow L by Dow W321, okay? Basically this by W321. I'm sure you would have guessed what it is. It's basically just Dow L by Dow O311 into Dow O311 upon Dow W321. Correct? It's the same because we have the same output over here, right? Similarly, if I want to go to from Dow W311 to Dow W211, right? If I want to go two steps, correct? How do I write it? If I have to write it as Dow L upon Dow W311, it's 11, right? Yeah. Sorry, Dow W211. Okay. I would write it as Dow L by Dow O31 to Dow O31 by Dow O21 into Dow O21 upon Dow W211, right? Similarly, if I have to write Dow L upon Dow W111, okay? W111 is this weight. So I'm going 1, 2, 3, 3 steps back. I'm going to write it as Dow L upon Dow O31 into Dow O31 upon Dow O21 into Dow O21 upon Dow O11 into Dow O11 upon Dow W111, right? That is my chain rule to basically find to basically find Dow L by Dow W11. Okay, so that's actually not correct. Why? Look, to get to Dow L by Dow one W11, this is so confusing. To get to Dow L by Dow W11, you basically have two paths, right? Let me just take a different color. Let me take orange. My one path comes from here, then it goes here, then it goes here, and then I arrive at Dow W11, right? The second path is that I come from here, I go down here, I come up here, and then I go this way. There are two paths to go to Dow W11. So this equation is not complete. I've only taken one path over here, right? I've gone this way. Now I have to go this way, right? So what I'm going to do is I'm just going to add the second formula, okay? I have this. I add to this Dow L by Dow O31 into Dow O31 upon Dow O22, right? This. Now Dow O22 to Dow O11 into Dow O11 upon Dow W111. Okay, this is actually my Dow L by Dow W11. Correct? Now look at this. There's something very peculiar happening over here. You see, I'm calculating the values of Dow L by Dow O31 multiple times. In all of these equations, I've calculated Dow L by Dow O31. Now over here, I've calculated Dow O31 and Dow O31 upon Dow O21 multiple times. So if you observe carefully, I've written only 5 equations for this. If you have a full-fledged neural net, you have a lot of equations, right? And computing the derivative is actually a very computationally intensive task. You know, it takes a lot of computation power to perform, which considerably slows your program down, right? Um, as you can see that, we are performing the derivative over here multiple times. O311 is being performed so many times. Dow L by Dow O31. Correct? This one. It's been performed so many times. Almost every equation will have it. So, and to save some computational time and power, why don't we store this value into some variable, like take an array or a dictionary and store it, and then when you have to compute it, just take that value from there and multiply it, right? That will considerably make your program faster. Because look, this is a simple three-layer network with GPUs and all. Today we can, it's fine, you can do it. But when you have hidden layers which are like 20 or 40 in number, as you see that there are so many architectures, deep neural net architectures that are very, very deep. Okay. And you can't possibly keep calculating the derivative over and over again. It's just faster and easier to store the value somewhere and recall it from that variable. This technique of storing, let's say, Dow L by Dow O31, which in the previous example was calculated every single time. If I take this and I store it somewhere, this technique is called memoization. Okay, this is the same memoization from your dynamic programming. If you don't know what dynamic programming is, it's basically a way to solve problems, a very efficient way, a very elegant way. But yeah, that's what it is. Memoization is just basically storing a value somewhere and calling it again, to avoid computing it over and over again, right? Yeah, that's what memoization is. So this thing that we've done, we calculate to find the weights, we find the derivative, and then want to calculate the weight, right? This Wij new is equal to Wij old upon Dow L and eta Dow L by Dow Wij1. Okay. So here we have chain rule and here we have memoization, right? Storing the values. So basically your chain rule plus memoization is called backpropagation. Backpropagation is the algorithm, it's the foundational algorithm behind all of deep neural net. Okay. It's just, when you first read backpropagation for the first time, you think that it's very complicated and stuff, but it's not. It's just chain rule plus memoization. Your 11th grade mathematics with just storing a value and retrieving it over and over again. This is called backpropagation. Okay. So now, once I do this, I just basically have to update my weights till convergence, right? I've written the formula over here. Update your weights till convergence. Okay. You keep doing this over and over again until you find out that your Wij new is almost equal to Wij old. That's when you stop your training. Okay, that's when you know that you've reached convergence or you're very close to it. Okay. Now, one important thing to note over here is that backpropagation only works if your activation function is differentiable. Activation function is differentiable. Okay. So look, you can have whatever activation function you want. You can have some arcane function from stochastic calculus as your activation function. But you need to make sure that it's differentiable. Okay, because if it's not differentiable, you can't possibly perform chain rule on it. And yeah, that's the reason why backpropagation won't work or it won't converge. Because if you take some arcane function where you can't perform differentiation and chain rule on it, you're lost. Backpropagation won't work. So you have to make sure that your activation function is differentiable. Okay. Yeah, so you basically have two very popular activation functions. They are the sigmoid function and the tanh function. Okay, so I'll just explain these two activation functions in this video, and then in the next video I'll explain what vanishing gradients and exploding gradients are. Okay, so your sigmoid function is basically just, if this is 0.5, and this is 0, your sigmoid function is basically just 0.5 to 1. Okay, this is your sigmoid function. And the differentiation of sigmoid, when you differentiate sigmoid, you get a graph like this. Okay, this value is about 0.25. This is your sigmoid function. And now, why do we choose sigmoid as the activation functions? Because it's very easy to calculate the differentiation of sigmoid. So if you have your sigmoid function as sigma, the differentiation of sigmoid is just sigma into 1 minus sigma, right? So if I have the function sigma, I can just subtract the value from 1 and multiply it. Then I take this value, this entire value over here, and then I multiply it as 1 minus sigma into 1 minus sigma. So, if I'm taking the chain rule over and over again, this is how you calculate the sigmoid function's differentiation. And that's why we take sigmoid, because it's just so easy to compute. Otherwise, if you have some very weird function that even if it's differentiable, you can use it. But the thing is, to compute the differentiation will take so much time that, you're just going to spend years training a model and you'll never reach convergence. So that's why sigmoid and tanh are very widely used for differentiation. So tanh is basically, look, the differentiation of tanh is basically 1 minus tan h square of z or x, whatever is this value. Okay. The differentiation of tan is 1 minus tan h the whole square, right? And the graph of tan h is basically like this. Okay, so tan h is basically the function tan h is like this, between 0 and 1. But the differentiation of tan h is basically, it's like this. It's basically, it goes from -1 to 1. Okay, this is -1 and this is 1. This is the differentiation of tan h. So I just want to draw the graph and show you how it works. You're getting confused in the color code over here. I'll just draw it as red. Right? So this is your graph for the activation function and their respective derivatives. Right?